Hello everyone, welcome to the first episode of Breaking Free from the Limitations of Arduino, or How I Learned to Stop Wiring and Love Bare Metal Embedded Development. So before I start showing you how to break away from the Arduino and its limitations, first let's take a look at why it's so popular in the first place. So one of the most important ones is that it lowers the barrier to entry for embedded systems development. It used to be that you had to have some coding experience, some hardware experience. A lot of the time you needed to be an electrical engineer before you could really get into embedded systems development. The Arduino platform totally changed all of that, and it made it much easier for just normal people to start in embedded systems development. The next is that it has open source hardware and software, and this is a big one. It means that you can make your own Arduinos hardware-wise, and you can also use the Arduino software. This is a big thing, which you can modify and change the Arduino software as you wish. But perhaps the most important one is that it creates a single, easy-to-use API across many microcontrollers from many different silicon vendors. And we'll go into APIs a bit more later. But so I've found 8-bit and 32-bit Arduinos. I'm sure there's a 16-bit Arduino out there somewhere. I haven't seen it, but I'm pretty sure there must be at least a few. So some of the architectures that are used. So the original architectures were 80 megas, and there was the 80 mega 328 and the 80 mega 168 were the original Arduinos. Now we also have 80 Tinies, we have a bunch of different PICs, we have ARM devices, we have STM32, Azure, NRF52, ESP8266, ESP32, SAMDs, MSP430s, and a whole bunch more. Even the venerable 8051 has an Arduino core written for it. So this saves you hours of digging through the datasheet, and digging through the datasheet scares off a lot of noobs. Some of the shorter datasheets for microcontrollers are around 300 pages. I've seen other datasheets that are 800 pages. This can be really, really intimidating when you're getting started. So the Arduino gets rid of that and makes it much, much easier to get started. Also, there are many libraries for popular sensors and interfaces ready to use just out of the box. You just install the library and you start using the device. It's that easy. And this is a huge selling point for the Arduino. And also, it makes your code easily portable across devices. This means that the same command needs only a slight modification to work on a completely different device. Whereas previously you would have to dig through the datasheet, you'd have to learn the register names, you'd have to learn a whole bunch of stuff before you could even transfer or port the code from one device to another. So I was talking about API calls before. So what is an API call? So an API stands for Application Programming Interface. Basically, it's a layer of abstraction between the hardware and the software that you're writing. And so in Arduino, some of the most common API calls are things like pin mode, where you set the as a pin as an input or an output. Then you have digitalWrite, where you can switch, for example, an LED on or off. Analog write, where you can control the speed of a motor. Then you have digital read, where you can read in from a switch or something else. Analog read, when you can read in from an analog sensor of some description. And then of course you have delay and millis, which are two commonly used ones. Now, these are great things for getting off the ground really quickly and getting started quickly, and they hide the underlying complexity of what's actually going on, and this is for better or for worse. So it is a double-edged sword. It can help you initially, but it can then hinder you later on, especially when you start getting weird behaviors going on and you don't know what it is because there's a whole bunch of things going on behind the scenes that you're not seeing. So Arduino is good, but this is a big one. So Arduino, as I was saying before, makes it really easy to get up and running quickly. And it's great for a proof of concept or for beginners getting started because it handles, as I said before, all of this stuff in the background. And so you can do things really quickly, or you can learn. It makes the learning rate much easier, the learning curve much easier for new beginners. And of course, that comes at a cost. So advanced users lose full control of the device they're using. And as a result, also, the Arduino API results in bloated and slow code. So for an example, a digital write on an Arduino takes about 2 microseconds, whereas an equivalent version of digital write on bare metal, and I'll go into later what bare metal is, but the equivalent controlling the hardware directly takes in the order of nanoseconds. So we're talking 3 orders of magnitude difference here. And similarly, a digital read takes 5 microseconds, and similar sort of thing for doing it when you're dealing directly with the hardware. Another big limitation of Arduino is you can only read or switch, that is control, one output pin at a time, or input pin at a time. And this can be a real problem, especially when you're trying to detect multiple things happening at the same time, because you can only do one read, you have to wait 5 microseconds for that to happen, and then you can do the next one. And for new beginners, 5 microseconds doesn't sound like a lot, but when you get more into it, you realize 5 microseconds is a long time in the world of microcontrollers. So, for all of you that have already been using Arduino, you're likely very familiar with the Arduino basic program skeleton here that I've got on the top left, where you have your void setup and you have your void loop. And in your setup, you put the code that you want to run once, and in the loop, you put the code that you want to run repeatedly over and over. But there's a lot of stuff going on there that you don't actually see. So just underneath that, I actually have a block of code that shows the equivalent from that. So first of all, we're importing the Arduino library, the header file, and then we actually have an int main void, which is a pretty common C file. And so we're actually calling inside that a function called init. And what does init do? Well, it turns out that it uses timer counter 0, or TC0, for millis, for micros, for delay, for controlling the PWM, which is your analog write. And so it sets up your fast PWM, your timer counter prescaler, enables the timer counter interrupts, and it enables your global interrupts. But this means that the user cannot use timer counter 0 for anything else. Arduino completely hijacks it. And so we see also after that, we have if defined USB con, then USB device attached. So it looks to see if there's a USB device attached, and then tries to run from there. And then it calls setup, and then finally it does the loop. And if there's any serial events, then it runs those. So already we see there's a fair bit happening without the user knowing. And if you want to dig around and find more of what, actually see the source code of what's actually happening in the init file, look up the file wiring.c inside your Arduino installation. Note that it is not the sketchbook area, that's the actual Arduino installation itself. You'll have to dig through several layers of the file system, but look for the file wiring.c. So, as I was saying before, a digital write on an Arduino takes somewhere around 5 microseconds. It was either 2 microseconds or 5 microseconds, I don't remember which. And this is why. On the left here, this is the source code of the digital write function. And we can see it does a whole bunch of stuff. It checks a whole bunch of things, like, for example, it checks whether or not you're actually trying to write to a pin that exists. It does all these tests. It does a whole bunch of stuff. Whereas if I want to just switch a pin high when I'm doing direct port manipulation, all I do is I write this one line on the right, which is port B, and I'm writing a 1 to bit 5. That's basically what that means, means I'm pin B5, I'm turning high, and that's it. So I have one line of code versus, that's got to be, what, 10, 15 lines? So already we can see why the Arduino is so much slower than doing direct control of the hardware. So let's go bare metal. So first, what is bare metal? Well, Bare metal just means that you're interacting with the system itself at the hardware level. That means there's no abstraction layers between you, the user, and the device. So the API calls that I was talking about before, they're abstraction layers. They make it easier to get up and running, but they're bloated and they come at a cost. So going bare metal means that you're directly controlling all the registers, the ports. You are in complete control, for better or worse. So with great power comes great responsibility. So this requires reading the data sheet. And a lot of people are scared about reading the data sheet. And it can be intimidating at first, because as I mentioned before, the ATmega 328p data sheet is almost 300 pages long. And people get scared by this, but everything you need to know is there. So I've got a link here for the ATmega 328p datasheet. So go and get yourself a copy of it, put it in your favorite PDF reader, and let's move forward. So when you start building your firmware, always build in stages. Don't just write the whole thing and hit compile and hope that things are going to work. Just like you build a house in stages, you also need to do the same thing with our firmware. So for this project, we're going to be flashing an LED. It's the old Blink sketch, except we're doing it bare metal. And so in order to do that, first of all, we're just going to turn an LED on and off manually. Once we've done that, then we're going to set up a timer, and it's going to toggle the LED. Step 3, of course, is profit. So, reading data sheets. So you need to know what you're dealing with before you start coding. If you just start coding without reading the data sheet, you're going to have a real bad time. So always read the overview first. That's a good place to start. Then read the electrical characteristics. These are very important. In particular, read the absolute maximums ratings. This tells you the highest voltage that you can put into it without letting the magic smoke out. For those unfamiliar, the magic smoke is what is let out when you destroy the device. So we also have typical characteristics. So this is things like how much current can an I/O pin sink or source? What is the active supply current at different frequencies? What's the idle supply current at different frequencies? What's the I/O pin threshold voltage at different VCC voltages? What's the brownout detection voltage at different temperatures? So these are very important things to know. Also, review the register summary, bookmark it, keep it, it's extremely useful. I'm constantly referring back to the register summary. And also, never forget, read the errata. I cannot stress this enough. This is vitally important because all the errors that have built up over time, they're all contained there in the errata. Read the errata, because if you're having problems and you can't figure it out, there's a reasonable chance that the answer is there. So, controlling an LED manually. So I'm going to use my Arduino Uno board, which happens to have a built-in LED on pin 13, as pretty much all Arduinos do. So note that pin 13 on the Arduino is not pin 13 on the ATmega 328p. These are not the same thing. And so I've got a screenshot here. So I have all the references at the end of this document. But we can see here, this is the Arduino on the left here, where we can see the Arduino pins. So we have AREF, ground, 13, 12, 11, and so forth. And then circled in red here, you can see that that's PB5, right? And that's actually connected to pin, it's dark there, but it's actually pin 19 on the ATmega 328. So pin 13 on the Arduino is actually pin 19 on the device, and that corresponds to port B5. Right, and we can also see over on the right here, we can see there's a symbol for an LED, so we can be sure that we've got the right one. But if you decide to use a different Arduino pin and a standalone external LED, you're going to need a current limiting resistor. Something in the realm of 330 ohms to 1 kilo ohm will work nicely. So then we need to set the direction of pin PB5, because we need to tell it whether it's an input or an output. Basically, this is the equivalent of using pin mode. So let's go to the datasheet and look for Chapter 13, I/O ports, because there are 3 ways to set up an I/O pin. It can be an input, it can be an output, and there's a third one called tri-state, which is high impedance, also known as high Z or Z, depending on where you're from. So high impedance, if you're trying to run a low power application and you're using more power than you think you should be using, go through all the pins that you are not using and set all of those to inputs high impedance. So it effectively turns them off and saves you power. So we're going to configure the pin. So as I mentioned just before, go to chapter 13 or section 13 and look for configuring the pin. Everything you need to know is there. So the 2 main things we need to know is DDR, which is the data direction register. So this is used to determine whether a pin will be set as an input or as an output. 1 is an output and 0 is an input. And we also have port XN, where X is the port, where it's A, B, C, or D, and N is the bit. And that's usually 0 to 7, but some ports have fewer bits. So let's look at some of these commands that I've written down. So first we have DDRB or equals 1 bit shift PB5. And I have a comment beside it saying set port B bit 5 as an output without changing any of the other bits. So that's what the OR equals does. It ORs this 1 bit shift PB5 with what's currently in the DDRB register. So it doesn't affect anything else that's in the register. The next one below it is DDRB OR equals 1 bit shift 5. So this is the same as above. So PB5 is actually an alias for just the number 5. PB5 makes it a little bit easier to read and also makes it a little bit easier when you're writing your code that you can be sure that you're doing the thing that you really want to be doing. It helps prevent simple errors from accidentally typing in a 4 instead of a 5. So the next line we have DDRB equals 1 bit shift PB5. So this is different to the previous ones because they were OR equals. This one is just straight equals. So this means it sets pin port B DDRB, so the DDR register, the direction register, and it sets bit 5 as an output and sets all of the others as an input. So that changes whatever else might be in those other bits in the register. So you have to be careful when you do this because you could be potentially overwriting other things that you've done and things might just suddenly stop working, and this could be why. The next line, so we have DDRB equals 1 bit shift DDB5. And the point of this, it's the same as the above, except again, DDB5 is also an alias for 5. So there are header files that are used that have all of these aliases in them, and it just makes the whole thing a little bit easier to read. Otherwise, you're just looking at numbers all the time and you're constantly referring to the data sheet. This makes it much easier to read, and then you can continue on with your day. So the next section, we have the actual setting the bits high or low in the register. So this is akin to turning an LED on or off. So the first one, we have port B or equals 1 bit shift DDB5. So this is set port B bit 5 high without changing any of the other bits. So remember, you can use DDB5 or PB5. They both point back to the same alias, which is 5. The next one is port B and equals not of 1 bit shift PB5. So this one, when you first encounter it, it might be a little bit tricky to get your head around it, but what it's actually doing is it's clearing the bit PB5 or port B bit 5 without affecting any of the other bits in the register. And so if you do it on paper, do the AND equals and then do the not of your 1 bit shifted P5, you can prove to yourself that it works. And then the last one, we have port B, I'm not sure what the correct term, hat, it's XOR. Port B XOR equals 1 bit shift PB5. And this toggles port B bit 5 without changing any of the other bits. So if port B bit 5 is a 0, it makes it a 1, and if it's a 1, it makes it a 0. Alright, so we have some basic code here. And so the first one, let's go from the top. We have include avr/io.h. So we're including the avr IO header file. Then we just have a normal C file skeleton there, which is int main void. And then we have ddrb or equals 1 bit shift ddb5. So we're setting up the direction register. So we have port B bit 5 and we're setting it to a 1, which means it's going to be an output. And then we're writing port B or equals 1 bit shift PB5. So we're turning on the LED at port B bit 5, which happens to be the Arduino pin 13. So when I do that, my LED comes on. Then the next one is, so we again have include avr io.h, and we have int main void. So the same ddrb is set up, and this time as I mentioned before, I'm clearing that bit. I'm using the and equals and then the not of 1 bit shift PB5. And then the third one, we have again the include for the avr io.h file. And then we're setting up a ddrb, our direction register, again exactly the same, and this time we toggle the bit. So each time we would upload that code, the LED would change from the state it was in currently to the next state. So if it was off, it would turn on, and if it was on, it would turn off with each time that we upload it. So you're probably asking, what's this include avr/io.h header file that we're using? Well, if you go and look up the source code, you'll find that it has a whole bunch of includes in it. And since we're using the ATmega 328p, one of the things it does is it goes and has a look and it says if we're using an ATmega 328p or if we're using an ATmega 328, then include this file avr/iom328p.h. So it's another header file. So our header file is pointing to another header file. And if we go to the source code for that one, it takes us to this. Now this is only a little screenshot of part of the code because there's actually quite a large file. And it just has a whole bunch of defines. And these are the aliases that I was talking about before. So we're defining ddb5, which is one that we were using, as 5. Which is what I was mentioning earlier. So this just makes it easier to read, as I mentioned earlier. So you can be sure that you're doing the thing that you want to be doing, and also the next person who comes along to maintain your code, it's much easier for them to figure out what it was that you were trying to do. And again, we also have port B5, the alias is 5. Port B0, the alias is 0. Again, this just makes your code easier to read and easier to debug. So now that we've got the LEDs all sorted out, the next thing is to set up the timer, because now we're going to get the timer to flash the LED for us. So I've decided to use timer counter 0 or TCNT0, and it's in chapter 14 of the datasheet. You could also use timer counter 1 or timer counter 2, but you would have to go to their sections in the datasheet as they are slightly different, the registers are slightly different, etc. But for the purposes of this, I'm using TC0, timer counter 0. So chapter 14.7 describes how TC0 has different modes of operation. And those modes are normal mode, clear timer on compare match, which is CTC mode, fast PWM mode, and phase correct PWM mode. So since we want to toggle an LED at a specific interval, and I've decided that it's going to be 500 milliseconds that we toggle, we will need CTC mode. So I've got a little screenshot from the datasheet. We can see here, so clear timer on compare match CTC mode, and it uses the bits WGM bits 2 to 0. If you set that to 2, then we have the OCR 0A, which is the overflow compare register timer 0A. It's used to manipulate the counter resolution. So in CTC mode, the counter is cleared to 0 when the counter value, TCNT0, matches that OCR0A value, and that defines the top value for the counter and also its resolution. This mode also allows greater control of the compare match output frequency. It simplifies the operation of counting external events. And we can see there's a timing diagram here just below that. And the counter value, TCNT0, increases. That's the ramp that's counting up until it reaches a compare match. And so we can see here the first few. So I've circled a couple of things here that are of importance. The first one is OCN, which is the output compare, and it toggles. So this is an interrupt flag that toggles. And the other one is the period of the timer. So you can see that output compare, that flag toggles. So when I say it's a single bit in a register, and so it'll go from a 0 to a 1, so that's the first toggle, and then it'll go from a 1 to a 0, that's the second toggle. And we can see here the period is actually 2 full ramps. Now this is important because later on when we do the math, if you don't take that into account, your numbers won't add up and you'll end up with something that's not quite right and it will take you hours to figure out. Okay, so now I have a screenshot of the datasheet which talks a little bit more about the interrupt. So just explaining that the interrupt can be generated each time the counter value reaches the top value. And that uses the OCF0A flag. That's the output compare flag for timer counter 0. And if the interrupt is enabled, then the interrupt handler routine then can be used for updating the top value. Now, we won't be updating the top value because we don't want to change it. We just want to keep it the same because we're doing a recurring thing. But you can change the timing of that each time it happens, but that's not of interest for this particular application. You can also generate a waveform output, but we're not going to be using that at this point in time. That will be used in a later project. But the thing of most interest to us here is that is this equation. So we have f of OCNX, and so I have just underneath this screenshot what the descriptions of what everything is. So f of OCNX is the frequency that we want the interrupt to occur. And that is equal to f clock IO, which is the clock frequency of IO, and we can change the IO frequency clock if we want, but for this we can do that in other registers, but I've left it standard at 16 megahertz. And then on the bottom of that we have on the denominator we have 2 times n times 1 plus OCR and x. So we already know what the frequency that we want the interrupt to occur at, and we also already know the clock frequency that we're going to be used for the IO clock. But there's 2 unknowns there. So we have to come up with 2 values, a combination of 2 values that will give us the output that we want. So there's a few ways that we can approach this. So the values we're looking for are n and OCR and x. And so different combinations will can have the same effect. So there's a few ways we can approach this. We can change the clock select to effectively slow down the timer counter 0 clock source, but we also lose resolution. Or we can use interrupts to effectively increase the duration of the timer without any loss of resolution. And so for the purposes of education, I've decided that we're going to use interrupts instead, so you get to learn something else as well. Okay, so now time for some maths, big brain time. So as mentioned before, we can use the timer to periodically trigger an interrupt, and then we count the number of times that interrupt occurs. And then we use that to toggle the LED, because the time period that we want in terms of microcontrollers is quite long. 500 milliseconds is a long time for a microcontroller. And so since we want to toggle the LED every 500 milliseconds, we need to find a number that's easily divisible, integer divisible, by 500. And so I decided on 4. 4 milliseconds is divisible, 500 milliseconds is divisible by 4 milliseconds. 500 goes into 4, 125 times. So nice and easy math there. And so what we can do is we can set our timer for 4 milliseconds, which corresponds to a frequency of 250 Hertz. Now, if you're unsure of the relationship between the period of the timer, that's the 4 milliseconds, and the frequency of the timer, that's the 250 Hertz. They are the inverse of each other. So that is 1 divided by 4 milliseconds equals 250 Hertz. 1 divided by 250 Hertz equals 4 milliseconds. It's really that easy. So the number of interrupts that we worked out was 125. That's 500 milliseconds divided by 4 milliseconds. So then back to this equation that we were looking at before. So we have our frequency of our output compare is equal to the I/O clock frequency divided by 2 times n, which is our prescaler, multiplied by 1 plus our output compare register top value. But the thing is, we want a full cycle. So this is what I was mentioning before. So you can see in this image here, we have OCX toggle circled in red. So that means every time the ramp counts up, it gets to the top, and then it toggles the output compare register and drops back to 0. And then it counts up again, and it toggles again. So that means if it starts at 0, the first toggle, it goes to 1. The second toggle, it goes back to 0. So that's 2 toggles for 1 period. And we can see here at the bottom, the second circle bit is the length of the period here, and that's the period of the timer. This is our 4 milliseconds. Corresponds to 2 count ups, to counting all the way up and starting again at 0. So we have to take that into account. Otherwise, our timer will be counting for a different period of time. It will be operating twice as fast as what we want. And so, coming back to this equation, since we have to take that into account, we have this equation here, and what we can do is we can just multiply that whole thing by 2. And since we already have a 2 on the denominator there, all we can do, since we're multiplying by 2, is just make that 2 go away. And so then, so we've multiplied with the frequency by 2, like both sides by 2, and so then we juggle some algebra, and we get out our OCR NX. Now in this case, since we are using timer counter 0, so that N is 0, and X is the compare register. So there's 2 compare registers, A and B. So we're using timer counter 0, so it's OCR 0, and I'm using the first compare, which is A. And so to get the value for that, I plug in my values here that I have. And so our clock frequency is 16 megahertz. And then I'm dividing by the prescaler. Now I looked at the prescaler on the timesheet and I decided to go for 256. You can use pretty much any combination of values as long as you end up with the same thing. So I've decided to use 256, and the other thing is the 250 Hertz, and that's the timer for 4 milliseconds that we mentioned before. So we plug, and then -1. And we plug that into a calculator, and that equals 249. So this is the top value that we're going to be counting to. So that's the top of the ramp. It counts up to 249, and then it drops back to 0. And then it counts up to 249 and drops back to 0. And that's all it is. So, interrupts. So as I mentioned before, timer counter 0 is going to be triggering an interrupt every 4 milliseconds. But we want to flash the LED every 500 milliseconds. So as mentioned before, all we have to do is count the number of interrupts, which we worked out was 125, and then we can toggle the LED. But we need to enable the interrupt, otherwise it's never going to occur. So from the data sheet here, I have a little screenshot from section 14.2.2 about registers, and the timer counter 0 and output compare registers, OCR 0A and OCR 0B, are 8-bit registers. So this means it counts from 0 to 255. And they have an interrupt request signal that are visible in the timer interrupt flag register, and the interrupts are individually masked with timer interrupt mask register. This is important, TIM-SK0. So we need to mask it in the TIM-SK0 register. So in order to do that, I will open up the data sheet to the TIM-SK0 page, which is section 14.9.6. And we can see the whole register here, all 8 bits of it. And we can see there's 3 bits that are available to us. So the one we're mostly interested in is OCIE 0A. That is output compare interrupt enable timer counter 0 compare match A. It's quite a mouthful. And all it says is that when that bit is written to the 1 and then the I bit in the status register is set, then that timer counter 0 compare match A interrupt is enabled. That's basically all it is. So we need to write to that bit in that register so that our interrupt will work. So now we have a list of the registers of interest for this project. So first we have DDRB, which is our direction register for port B. Then port B itself, in which bit 5 is connected to Arduino pin 13. Then we have the TCCR 0A register, in which you need to figure out which bits to set to use the CTC mode. Then OCR 0A, so you need to set the top value that we calculated in the equation earlier. So you need to write that to the register. Then we have timer mask 0, so we need for the timer counter 0 output compare match interrupt enable, otherwise your interrupts will not work. And then also the TCCR 0B, which is setting the clock select prescaler. And that one is important because that one also starts the timer counting. So when you're writing the code, that should be the last one that you call in order to trigger the counter or the timer to start counting. So interrupt service routine. Interrupt service routine, or ISR, should be as short as possible. This is because if you have multiple interrupts that are happening, if your interrupt service routine is long, you may not get to the end of it before the next interrupt is called, and then you can get some undefined behavior occurring. So you really want it to be as short as possible. Generally, what I will do in an ISR is I use the ISR to change a variable, whether it's incrementing a counter or setting a flag or something really simple and quick, and then get out of the ISR so that you're ready to deal with the next one that comes along. Do not have lengthy statements, for example, if-else statements and switch case statements and things like that. Keep it short and sweet. Do not use any form of delays in there. That's a nightmare. You're going to cause all sorts of problems. Now the other thing is we need to tell the ISR which interrupt vector we're going to use, because there are a lot of different interrupts. So each one uses an ISR to tell the microcontroller how to handle the interrupt. So we have on this page here in section 11 of the datasheet, it's the interrupt vector table. And so we have the vector number, we have the program address, so that's where the program counter jumps to when that interrupt is triggered. What the source is, in this case we can see circled in red, we have timer 0 compare A. And so that's the interrupt that we're using, timer counter 0 compare match A. So take note of that, timer 0 comp A. So I've decided to write basically the whole interrupt service routine for you because it can get a little bit tricky. Now, since the ISR is counting to 125 for us, an important thing to know is when we define the counter variable, we need to use the volatile keyword. So this is a compiler directive, and it just tells the compiler to get the value directly from RAM and not get it from a storage register, because it is getting changed since the storage register, or potentially being changed since the storage register has last accessed it, and so the value there may not be the actual correct value. And as we noted on the last slide, the ISR source is timer 0 comp A. So first I have an include line of code here, AVR interrupt, so it knows where to go look for this information. And then here's the ISR, so we have ISR timer 0 underscore comp A underscore vect. So that's our ISR vector telling it which interrupt that it is going to be servicing. So when that one is called, it goes and looks it up and says, this is the one I want, and then executes the code in this block. And we can see here, I actually only have one line of executable code, and that is incrementing the counter, and that's it. And then we get out. So you want it to be as short and sweet as possible, as I mentioned before. And this ISR is occurring every 4 milliseconds. So I decided to include a code skeleton for you here to make your first steps in bare metal embedded development a little bit easier. So do not use Arduino's setup and loop functions, because setup, as I mentioned earlier, does things in the background which, if you don't know what they're doing, they can really mess with what you're doing, and things will either not work properly or not work at all. So instead, use the C++ or C code skeleton that I have here. And so I'm just going to go through it with you. So starting from the top, we have include AVR IO and include AVR interrupt header files. So that just enables you to use the port names and also to use the interrupts. Then we set up the volatile counter, which, as we discussed before, and this is an 8-bit counter, and we initialize it to 0. Now I'm going to quickly jump to the bottom where we can see I have the interrupt service routine. And in that, all we're doing is incrementing the counter. That's the only executable code in that block. So then jump back up to the middle, and we have int main void. So in that, there's a comment saying do your register setup here. So set all your registers, and then while one. Now while one is the equivalent of Arduino's loop function. And this is where you're going to take a look at the counter variable, and if it has met or exceeded the value that we looked at earlier, which was 125, then we will toggle the LED. And if it does meet or exceed that, then you need to make sure that you reset the counter. Now you have everything you need to set everything up, but let's take a look at some important notes. To enable global interrupts, you need to use this command, SEI. It's calling a function. It enables it sets the global interrupt mask, enabling interrupts across the whole system. Now this should be done immediately prior to setting the timer counter 0 prescaler, because when you set the prescaler, it also starts the timer peripheral. This is very important. So starting the timer peripheral should be the last thing that you do in the register setup before going into while one. And there's a link here just below that, and this is actually the AVR user guide, basically user manual. There's a lot of really good information there. So if you ever run into problems, I would highly recommend bookmarking this. This is super useful. So now you're ready to go and write the code. You have all the information you need to finish this. It's about 10 lines of code to do this. So we've gone through the data sheet, we identified the registers. Now you just have to figure out the last steps on your own. If you have questions or comments, please drop them in the comments below. If you enjoyed this video, please give me a like or a subscribe. Thanks for watching. Also, here are the references that I've used throughout this, mostly for images, but there's also the data sheet and also the list of Arduino compatible devices that I used. Thank you.